Good afternoon, sir. Good afternoon to all.
Yes, Yatin, good afternoon.
Myself, Dr. Vidya Kansukla, sir.
Okay, Vidyakar.
So now I am going to welcome and introduce a very renowned professor, a man of invincible courage and endurance, Dr. Sanjeev Rai, sir. It's my esteemed pleasure and profound honor to welcome Professor Dr. Sanjeev Rai, sir. Dr. Sanjeev Rai, sir, the faculty of the Department of Electronics, Motilal Nehru National Institute of Technology, Prayag, has been an eminent teacher and legendary scholar, imparting his wide experience and knowledge in the field of electronics engineering. Professor Rai has done his doctoral from MNIT Allahabad. His area of interest includes semiconductor device, modeling, analog, VLSI, design, nanoelectronics, low power, low voltage, circuit design, VLSI circuits and system, and has got wide research papers and journals published in all major journals. His research work is very useful in the field of science and engineering. He has a vast experience of teaching to the UG and PG students. Overall, it can be said that the interest and the contribution of the Professor Dr. Sanjeev Rai sir has made him a bright star in the field of science and technology. Now, I would like to call Dr. Rai sir, please come and enlighten us. Voice नहीं आ रहा.
Sir, your voice is not audible, sir. Sir?
Yes. It was mute. So, thanks for such encouraging word, Dr. Shukla.
Yes, sir.
And I was very much touched by what you just now said. But
Thank you, sir.
being a teacher, our primary objective is to teach our students. But apart from that, since the things have prevailed in such a manner that research now has become an integral part of all of us. So I hope my today's lecture would generate some information for the students and teachers who are here as a part of this lecture series. So yes, this is what I have to say. Now,
Thank you, sir. Thank you, sir.
so shall we start, or do
Yes,
you?
sir, you can start, sir.
We can start now.
Yes, sir.
Okay. So I'll just share the slide first, and then we can start. I hope this is visible to everyone.
Yes, sir.
Okay, fine. So the slides are visible?
Yes, sir.
Okay, fine. So let us start. So today's objective would be to dwell upon the recent trends in VLSI design, and we would be primarily focusing on the leakage control and the low power design issues. Now we have, it has been very, lately it has been very difficult for the design engineers to look out for the field in which they would like to work. And normally what we have seen is that the present scenario has changed in which way we look at the technology advancement which has taken place shortly. So in this respect, what VLSI has done is that the device size has considerably been reduced to a very small size. And these miniature size, as you all will agree, that these miniature size of devices not only affects the performance of the device, but also, as we have known for years, that more and more number of devices are being fabricated on a single chip. So this subject or this concept of VLSI, once emerged, has gained a lot of momentum, and still that momentum is persisting. And it is the encouragement to the students and the excitement which the student or the researchers feel to work in this field is what driving this further. But as we all will appreciate that the size of the transistors have come down to considerably low dimensions, and working at those dimensions is again a very big challenge for the design engineer. So considering considering this aspect, as we have just now discussed, now it has been very important to note that this technology advancement which has taken place has has taken place simply for the reason that the devices, or the electronic gadgets which we take in our hands and use them for our advantage for various purposes, has given lot of importance. So handheld devices, which we which may be a mobile phone, which may be a laptop, even a laptop, we can keep it on our laptops, tablets, and there are so many other devices which are electronic gadgets which are in the market, which and all these devices are very much power hungry devices. We all have understood and we all know the importance of the battery and the power consumption in these devices. Now, why is the power consumption so important? It is important for us to know. The reason is that, as I said just now, that these handheld gadgets or devices are power hungry devices. That simply means that these devices consume a lot of power. And lately, we have seen that the mobile phones, which are Android, they consume a lot of power. The reason for a lot of power being consumed by these devices is that the number of applications on the mobile phone or on the device is numerously large. Today, I don't think there would be a person who would not be having a handheld Android phone. And if he has an Android phone, there is ought to be number of applications on those phones. So at least handful of them we use it, but there are so many other applications which are of no use to us, but still they continue to operate in the background of the device. And this is what consumes a lot of power in these devices. So battery maximization, when we are talking about, or maximizing the life of the battery, when we are discussing about, it is important to note that how do we maximize the battery life. So in order to maximize the battery life, there may be multiple alternatives, but the two important alternatives which come to the fore are: one, either you go ahead and improve the battery itself, and if you can do that, that would be fantastic. So that means you are for increasing the life of the battery and by increasing the technology which is in use. But on the other hand, there are also other techniques, and the method which is more prominent here is maximizing the battery life by maximizing your operation by removing the applications which are of very less or or are of no use to us. As I just pointed out a minute before, that our mobile phones or the gadgets have a lot of applications, and those applications run in the background. knowingly or unknowingly, they run in the background. Once you run, by default, they run every time when you turn on your device. So why not clean our mobile phones and keep only those applications which are important to us, and that would certainly maximize the battery life or maximize the battery usage time. This is very important for all of us to think, because these are power hungry devices. The battery itself is improving a lot. Lithium ion batteries, they are giving a lot of usage hours to us. But still, when we start using the mobile phone, the mobile drains out fast because we are using the mobile a lot. And this is one very important aspect on which lot of research is going on. So probably even the research scholars or the research students can think about maximizing the battery life by any other means. So there are numerous circuit techniques by which also any redundancy which is present in the circuit can be removed, and circuit power consumption can be minimized. But please note, not always removing the redundancy from the circuit would result into better performance, because sometimes redundancy is important in the context of the circuit operation. I hope this is clear to everyone. Okay. So having said that, yes, one other thing which other important thing as regards the battery life is concerned is that numerous techniques are being developed by which the energy can be recycled in the battery. So still the technology, not, I should not say technology, but this is in a very nascent stage, but researchers can look to works on recycling the energy in one or the other forms in the battery. So we can think about this as well. Further, now it is important, lot many times this question comes to us, why low power consumption? Some of it we have already discussed, I've already discussed with you, but yes, to name some of them, several reasons underline the emergence of this issue. Battery operated portable devices require more battery life. Yes, that is very true. We have just now discussed. Reduction of power for high performance systems. Now you see, it is important to note that high performance systems always consume lot of energy and lot of power. This power consumption, if one way or the other, without affecting the performance of the system, if this can be achieved, this would be remarkable for the device power consumption or the overall power consumption of the of the system. So this is something which is very important as regards high performance systems are concerned. And also please note that this is not only the high performance systems, but also note that these high performance systems, when they operate for longer durations, they get heated up. So better heat sinks also have to be provided so that the devices can be cooled off at appropriate times. And it is important in this context that not only does the circuit be prevented, but also the performance is not affected. So both the things have to be taken into considerations, and simultaneously they have to be achieved. So optimization is something which is very important as regards these are concerned. As regards the power consumption is concerned, performance is least affected, as well as the power consumption is also low, comparatively low. With high power dissipation, reliability is an issue. Just now I discussed that what happens if power consumption in the circuit or in a device increases, what happens? Or if the device is made to operate continuously, what happens is that the device heats up. So either you have to cool off that device Otherwise, what will happen? We have already studied, and all of us very well know, we all are engineers, that for every 10-degree rise in temperature, the reverse saturation current almost doubles. So keeping this in mind, any increase in or rise in temperature is something which has to be taken care of, and device has to be made to be operated in an in or around the room temperatures, which makes it convenient for the not only the design engineers but also the end users to use the device. So reliability is a very important issue. Please note, not only does is this related to the temperature, but also to the environmental noise or the nearby noise or the industrial noise. We all are very much aware of that noises normally are of two types, and to categorize the noise, we can categorize them into two different parts: external noises as well as internal noises. External noises obviously are affected due to the atmospheric effects, your cosmic effects, so on and so forth. Whereas if it goes to internal noises, we know that there are other very prominent internal noises which affect the circuits, and they are thermal noise, short noise, flicker noise, and so on. And there may be some others also, but these are some of the important internal noises. Thermal noise, you all know that thermal noise, wherever a conductor or resistance is found, a thermal noise is bound to be present there. So thermal noise has to be taken care of. Then short noise, obviously at high frequencies. Then comes the flicker noise at low frequencies. Flicker noise is also known as 1 by F noise. If you would have studied the noise, uh, you must be very much aware of it. So noise is also very important. So reliability is something which is very important for the proper operation of the circuit and the device. So it is important that when such circuits are designed, always lot of emphasis should be to cool off the circuit as and when required, because there may be certain part of the circuit uh, which operates for longer durations. Yes, please note that whenever such type of circuits which require lot of longer duration operations, these circuits, sometimes alternatives may be thought of and redundancy may be introduced. But if redundancy is not being introduced, then alternative mechanisms may also be thought of, and those alternative mechanisms may be to cool off the circuits, maybe to use a very good isolation techniques to isolate the circuit from the atmosphere, so on and so forth. So there may be various ways by which this can be achieved. So reliability has to be taken care of. Next, since the usage of electronic equipment is increasing at an alarming pace, hence power hedging has to be done to limit the power consumption. Yes, we've already discussed this. And just to add to this, power hedging, now this word actually is propping up, and we are coming to terms with these words, power hedging types. So please note, power hedging is synonym to how much power we can conserve, or how much we can conserve, how much we can uh, make the circuit consume less power. So this is directly related to that, and this is being achieved through various measures. Your measures may start even at the level of writing a program. So if you can efficiently write a program, there also you can very successfully power hedge. I hope this is clear. Okay, and further, the final one. Aging effect may reduce the effective life of the device. Yes, this is very important, and important in terms of the life of the device. Now, please note that when the device is subjected to operation and for elongated hours, or for that matter, if the device is made to operate for longer hour durations, under that circumstances, it may so happen that wear and tear will start happening in the device very soon. So aging effect is something which is not only related to the living substances like human beings or animals. No, this affects the devices as well, whether it is a mechanical device or an electronic device. Aging effect has to be there. There is supposed to be wear and tear as the time passes by. So aging effect is something which has to be effectively optimized. When I say effectively optimized, that simply means that uh, if you've designed a circuit. Now I would just relate this to the devices, just but let me first complete the sentence, then I'll go through. Please note that if the device uh, if the device is made to operate for longer duration of hours, under that circumstances, what happens? Device hardly gets time to relax. So under that circumstances, what happens is that suddenly power consumptions also increase, leakages increase, and the device performance degrades. So it is important that either you break away for some time for the device and alternately shift the operation onto some other redundant circuit or use some alternative mechanisms, because under that circumstances aging effect would creep in very fast and that would degrade the performance of the subjected device. So please note, this also is one of the reasons why redundancy in the circuit is preferred, and redundant circuits are also used in the circuit designs. And it is important. It is important for us to remember or understand this. Now, also note that when we are saying or when we are discussing about redundancy, then please note, for a short duration advantage, you can remove the redundancies. But what happens? The effective life of the device reduces. And today, you know that the devices, your handheld devices which we are using, they are very costly devices, even our mobile phones. But even though they are costly, their life shelf is very small, and every 2 to 3 years we change our mobiles because some or the other problems creep in. So please note the time period of the or the effective life of the device which we are using is a very short time. I hope this is clear. So these may be some of the reasons, and this is how the cost effectiveness of the device also comes into picture here. Sometimes we feel like that why some of the producers, some of the mobile manufacturing producers, they come up with mm, mobile phones with all the features with with the not so costly devices. It means they're not so costly. But on the other hand, there are certain brands which are very costly, and they can be differentiated, and it's very easy for us to differentiate. The reason being that the quality of the quality of hardwares and softwares which is used there may be of very good standard, and that would also be related in terms of longer effective life of the device. This is also one of the very important reasons which can be felt or understood. Okay, moving ahead. Why leakage power? Okay, this is another very important aspect which lot of us always tend to ask among ourselves and try to understand as to what this leakage is. Now, in order to define a leakage, I think this is something which we have long back learned in terms of the reverse saturation current, or it's a very small current which is flowing through the circuit, which is of less significance. But actually, when that small current multiplies to some extent, that may even damage the not only the circuit but also the device. So the small current which continues to flow even at the gate voltage is reduced below the threshold voltage of the device constitutes a static power consumption dissipation called leakage power. Now, in order to understand this leakage, please note that this constitution of leakage, there are various ways. We will come to that later on. And we will see that how different leakages can be understood or can be formed. But first, try to understand what this leakage actually is and how this is formed. Whether it is a BJT device or a MOSFET device, these leakages are, as the name itself suggests, leakages means something getting leaked out, something getting leaked out from somewhere. So here the current is getting leaked out, isn't it? And this magnitude of the current is very small. Or for that matter, please note, where will this leakage current or small leakage current would be formed and would be identified? Obviously at the PN junctions. So please note, wherever PN junctions are formed, leakages are bound to be present at that place. So we know that when we are using a MOSFET, we are using a substrate. If we are using a substrate of P-type, then we are using two N-type of diffusion regions. So two N-type of diffusion regions, whereas gate also is there. So lot of PN junctions would be formed. Substrate to source, substrate to drain, then substrate to gate, then gate to source, gate to drain, so on and so forth. Lot of junctions would be formed. Lot of junctions, not always PN junctions, but lot of junctions would be formed. And some of the PN junctions, or most of the PN junctions which are formed here, they would constitute some current to flow across them. And this constitutes leakage power. Now, any current which is less than the threshold voltage is assumed to be a leakage current, isn't it? Less than the threshold voltage is assumed to be leakage current. And this leakage current is a small current. We have just now identified and we have just now stated this. Now, the threshold voltage has been defined here, where flat band voltage, surface potential plus bulk charge divided by oxide capacitance has been shown here. There are number of other threshold voltage equations which you must have studied and you must have dwelt upon. And for that matter, it is important to note that the threshold voltage depends on various factors, and some of them have already been outlined here. And here, prominently, the bulk charge, okay, the bulk depletion charge, QB, divided by the oxide capacitance. So if you wish that the threshold voltage should be small, make the oxide thickness large, okay, so that the threshold voltage will be small. But what is happening here? Nowadays, the oxide thickness are also getting reduced. Simultaneously, the bulk depletion charge. Bulk depletion, the threshold voltage directly depends on or directly proportional to the bulk depletion charge. Flat band voltage as well as the surface potential, obviously, it depends on them also. Now, this is also something which is important to us. As you know that the power supply voltage is getting scaled. Now, before that, let me very briefly, because that would come at a later stage, briefly tell you about the scaling. Now, see, broadly speaking, I hope everyone can hear me. Please respond, anyone. I hope everyone can hear me.
Yes, sir.
Okay, fine. Thank you. So, broadly speaking, this scaling can be divided into two categories: constant voltage scaling as well as constant field scaling. Normally what happened during long channel devices was that at that instant of time constant field scaling was preferred and the voltages were scaled, because the voltages earlier used were pretty high voltages, and those high voltages were uh, of the order of 5 volt or even 3 volts. Some of the devices which are using today are even up to 5 volts or up to 12 volts in some cases. So long channel devices, the power supply voltages were higher. So at that instant, there was all scope to reduce the power supply further. So a constant field scaling was used where the voltages, power supply voltages were also scaled. And among the other parameters, the power supply voltages were also scaled. Now, when the power supply voltages were also scaled, obviously scaling down the power supply voltages would certainly bring down the power consumption in the circuit. Okay, but what happens here is that you need to study the other factors and other parameters also in tandem with the scaling of the other parameters corresponding to the power supply being scaled. So as the power supply voltage is being scaled to improve the energy per operation, the MOS device's threshold voltage must also be scaled. Yes. So you are scaling down the power supply voltage. So if you are scaling down the power supply voltage, then obviously the threshold voltage also is subjected to scale. And this also scales down. Now, when the threshold voltage actually scales down, and now in the present scenario, when the devices have become very small for short channel devices, the threshold voltage also gets scaled accordingly. And this further scaling down of the threshold voltage would exponentially increase the device threshold leakage current in the device. And this we cannot ignore. In long channel devices, we had successfully ignored this because as compared to the power supply voltage, higher power supply voltage or the current of the device, minimal current or the voltage was very small. But since the power supply voltages have been further scaled down to such levels, sub 1 volt level or 1 volt level, so that even a very small leakage current cannot be ignored, because that becomes comparable to the current which is flowing in the circuit. I hope this is clear to all of you. So this is the reason why scaling down the power supply voltage in the present day scenario is becoming more and more difficult. Because just imagine for a moment that if you have scaled down the power supply voltage to 1 volt or even less than that, 0.6 volts, isn't it? The threshold voltage itself is around what we have learned is 0.5 to 0.6 volts. But yes, as I've said, here the threshold voltage is getting reduced, so that would also come down. That would have come down. But please remember that the environmental noise or the other noises put together, they are if they are summed up, the noise potential would also come out to be primarily equal to 0.2 to 0.3 volts. So is your power supply not getting closer to the noise potential? Yes. That is the reason why it is becoming increasingly difficult to scale down the power supply voltages further. So that is why in the present scenario, we are using a constant voltage scaling types. Okay. So as and when the design engineers think that it is necessary for a specific technology to have a constant voltage scaling type, they go for that. Or for that matter, if some other design engineers, based on certain applications, think that constant field scaling is required, they would go with that. Now, there are so many parameters on which these aspects are dependent, and the design engineer has to take a call. So, the scaling factors are responsible for them to take the decision. Okay, moving ahead. Again, the short channel devices are when do we call the MOSFET as short channel devices? I've already explained, but you can further go ahead and here. A MOS transistor is called a short channel device if its length is of the same order of magnitude as the depletion region thickness of the source and drain regions. In technical terms, in theoretical terms, this is how a short channel device is defined. If its total channel length from source to drain becomes comparable to the sum of the depletion regions of source and drain junctions, then we say that a short channel, this is a short channel device, or this will lead to a short channel. I hope this is clear. So the short channel effects are attributed to two physical phenomena. This is important. Sometimes, or many a times, these questions have been asked in certain competitive examinations. So the first, limitation on the electron drift characteristics in the channel, and the second one, reduction of the threshold voltage due to shortening of the channel length. I think both are self-explanatory, and we have already stated this. So limitation on the electron drift characteristics in the channel and reduction of the threshold voltage due to shortening of the channel. Please note, one thing I would like to highlight here is that with short channel devices, yes, please, just a minute. Threshold voltage short. With this short channel devices, another very important aspect to note is that when the devices are becoming, when we had used long channel devices, or when we had studied bipolar junction transistors, or when we had studied a carrier transport phenomenon, we had stated that the classical transport phenomenon actually can be applied to these devices. And in that case, what had happened was the electron was made to uh, 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 pass at least the mean free path. The electron was made to travel at least the minimum of the mean free path before any recombination taking place, or for that matter, for any other condition. But what has happened today is the device size has become so small that, and it has become so comparable, that now it becomes difficult for the natural phenomenon to be continued. When I say natural phenomenon, that simply means the your classical transport phenomenon. So when the device size has become small, you just imagine if the channel length becomes comparable to the mean free path of the device, what will happen? This will put a limitation, isn't it? The classical transport phenomenon cannot be applied to the device. So these are some of the limitations, and that is where quasi-ballistic and ballistic transport phenomenon has to be taken into consideration for short channel devices. The same thing, just this represents the threshold voltage with reference to the effective channel length, and this is what we have understood, that with decrease in effective length of the channel, the threshold voltage or the threshold reduces. This happens because of the depletion region associated with the source and drain regions protrude into each other's channel area, thereby reducing the immobile charges. So if the number of immobile charges reduce, what will happen? Obviously, the threshold voltage would reduce, because we have seen that in the threshold voltage equation, the depletion charge QB was. So this immobile charges reduce would further reduce the effective depletion charge, thus reducing the threshold voltage. Okay. Now coming to the short channel effects, the various short channel effects which we have studied and which we have uh, come across, and we know that these devices, since they are short channel devices, so obviously the short channel effects have to be understood and they have to be taken care of, because without that the purpose would not be solved. So this DIBL, this is popularly known as DIBL, drain induced barrier lowering. This is a short channel phenomenon, as has been stated here, where the threshold voltage and the subthreshold current of the short channel devices vary with the drain bias. So obviously, at higher drain biases, what happens? DIBL effect can be observed. And this is a phenomenon where the threshold voltage vary with the application of the drain bias. Okay? And not only the threshold voltage, but also the subthreshold current. So this is something which is very important. This drain induced barrier lowering obviously also further reduces the threshold voltage and increase in the subthreshold current. So any increase in the subthreshold current and with reduction in the threshold voltage obviously would result into increased threshold voltage, increased leakage current. Please note, increased leakage current and hence further increased power consumption in the circuit. So DIBL actually is a phenomenon which is present only in short channel devices, and this is not present in long channel devices. And actually, this is absent in long channel devices. This has been explained here further. You can very well see the graph at the bottom, which shows for different drain to source voltages at low drain to source voltage as well as higher drain to source voltage. So you can see that higher drain to source voltage causes the threshold voltage of the channel to decrease, which has been shown in the graph. यहाँ पे आपको कम दिखाई भी दे रहा है. Okay. So again, uh, both the effects have been shown here, where the channel length and the threshold voltage for the different drain voltages have been shown here. For a low drain voltage, obviously, the short channel effect is present. But when when DIBL effect starts to creep in, what happens? This starts to creep in at high drain voltage. So low drain voltage, only the short channel effect, which was prevalent. Some of the other short channel effects which would have been prevalent even at the low drain voltages will be present. But as the drain voltage is increased, what happens? DIBL effect also creeps in, and that further lowers the threshold voltage. You can see reduction in the threshold voltage. तो सिर्फ short channel effect की वजह से just by scaling down the devices, the threshold voltage also reduces. But if DIBL is present, that further reduces the threshold voltage. This is what has been shown. I hope you have understood this. This graph is important for us to understand. Please note. Here, reduction in the threshold voltage has been shown with respect to both the short channel effect as well as DIBL. So if we consider simply the short channel effect, it means shortening of the channel length. Under that circumstances, we can see that the threshold voltage reduces if the channel dimensions are further reduced. But what happens is that if a high drain voltage is used during operation, that would further reduce the threshold voltage. As we have seen that any increase in the drain voltage would obviously vary not only the threshold voltage but also the subthreshold current. So DIBL creeps in at higher drain potentials. I hope this is clear. Okay. Now, having said that, further moving to the some of the other short channel fields. Velocity saturation. Now, when we consider this velocity saturation, this also is one of the causes of short channel effects. Now, what happens here is that if a strong electric field, now when we have applied a high drain potential or a high drain voltage, what happens? Obviously, the electric field would be high. Okay. Now, when the electric field would be high, what will happen to the carriers? The carriers' velocity would also be very high and would reach a maximum value at a certain speed. Okay. This is known as saturation velocity. Okay. And under this circumstances, we say that the device has reached saturation, velocity saturation. It means with any further increase in the potential to the drain, there is bound to be no effect on the velocity of the carriers which is being moved from source to drain. Okay, I hope this is clear. So the velocity saturates here and there is no effect altogether of any increase of the electric field or the potential at the drain. Okay, and this is important to note that uh, why this happens. This happens simply because when you increase the drain potential, what happens is that the carriers are moving along from source towards drain. So what will happen here is that those carriers actually will go ahead and interact with the lattice either at the surface end or at the lower end, maybe some of the carriers, and there they would lose their energy, okay, due to the interaction with the surface or with the lattice. So this results into velocity saturation. And this velocity saturation obviously happens at very high field, which is present due to the application of high drain potential. This is what has been shown here. As you can see from the graph depicts very well here how the with the increase in drain to source voltage without velocity saturation and with velocity saturation. As you can see, without velocity saturation, the drain current is higher, okay, and with velocity saturation, what happens? The drain current lowers, whereas the threshold voltage also reduces. Sorry, the drain to source voltage at a lower drain to source voltage, the saturation takes place. Okay, I hope this is clear. So velocity saturation, obviously, with the application of the drain potential, this graph depicts the uh, uh, how they behave. Okay, now further coming to uh, this, I hope everyone uh, can hear. किसी को कोई problem तो नहीं है? Any questions or something of that type? Nice. Okay. So let us continue. Fine. Okay. So continuing with what we have been studying, as I've been elaborating again and again, that power consumption is very important in these devices. And any power which is being consumed obviously would uh, uh, result into either aging effect or in some way or the other, if the device is being operated upon for longer durations, that would also affect the performance of the device. So it is important for us to analyze power consumption in the circuits at a greater detail. So in this slide, as you can see here, there are various leakage currents which are present in the MOS devices. And these leakage currents are very important leakage currents. And they have been summarized here, and we will see each of these currents one by one. But before that, let us see this. Yes, let us see this. Yes, let us see this. As you can see here, this is a MOSFET, simple MOSFET. The substrate, the source, the drain, the gate, all terminals have been shown here. And here you can see some lines drawn, and they have with subscripts I1, I2, I3, I4, I5, and I6. These are leakage currents, which I have just now shown. These leakage currents, which we will see. So I1 obviously is the leakage current due to PN junction. I2 is the subthreshold leakage current. I3 oxide tunneling current. I4 current due to hot carrier injection. Let us see first I1, I2, I3. I1 reverse PN junction current. I2 subthreshold leakage current. See here, I1, this is reverse PN junction current, okay, and I2, this is the subthreshold leakage current, and this I3 is oxide tunneling current. I4 gate current due to hot carrier injection. I3 and I4, they have been shown with a single line, but actually both are different. One is the tunneling, and another one is due to the hot carrier injection. I'll tell you the difference between these two very shortly. But I3 and I4, this is how I3 and I4 can be understood. I5, gate induced drain leakage, GIDL, gate induced drain leakage, and I6, channel punch through current. I6 is this channel punch through current, when the two channels almost meet each other. Under that circumstances, I6 can be created. Okay, I hope this is clear. So these are the 6 leakage currents which can be understood here, and these leakage currents primarily play a very important in deciding how much power consumption is taking place in the circuits. Now, having said this, it becomes again very important to note that these currents which we are discussing right now, these currents, whether they can be modeled, yes. All these currents actually have been modeled by using semiconductor device model. And all these currents have not only been modeled, but they have also been theoretically or analytically proved. So this is the importance of all these leakage currents which are present. Prominently, these are 6 in number, and all the 6 leakage currents, I1 to I6, constitute leakage currents, and they constitute power consumption in the circuit, in any circuit. So let us see one by one. I1 is the reverse bias PN junction leakage current. What it is, as you can see here. If both N and P regions are heavily doped, band-to-band tunneling dominates the leakage current. That's very true. High electric field across the reverse bias PN junction results in tunneling of electrons from valence of P region to conduction band of N region. I think this is pretty straightforward and understandable. Or in very crude language, you can understand that wherever a PN junction is formed, a leakage, junction leakage current would be present. Okay, a junction leakage current would be present. Next, I2, subthreshold leakage current. Now we know that when the device is operating below the threshold voltage, what happens? When the device is operating below the threshold voltage, obviously, in, in technical terms, we say that the device is still not on. Okay, the device is still not on. So when will the device be on? The device will only be on when the applied gate to source potential exceeds beyond the threshold voltage. And that is a threshold voltage. Though the exact boundary of the threshold voltage cannot be properly defined, but yes, we know that this is somewhere closer to zero point 0.5 to zero point 0.6 volts, zero point 0.6 volts for long channel devices. So in long channel devices, the subthreshold current is independent of drain voltage. We normally voltage for VDS larger than view threshold voltage, but has exponential dependence on gate voltage. Okay. In short channel devices, the leakage is derived due to short channel effects described, as we have seen earlier. Now, the following effects, DIBL, body effect, narrow width effect, channel off, effect of channel length and VTH roll off, effect of temperature, so on and so forth, all these may affect the threshold voltage, threshold, subthreshold leakage in one way or the other. So please note, subthreshold, as far as subthreshold leakage I2 is concerned, all these effects actually may lead to subthreshold leakage, whether it is DIBL, body effect, narrow width effect, effect of channel, or VTH roll off, or effect of temperature. All these combined together, or individually, or in combination of one or two, they may result into subthreshold current. And this subthreshold current is a very important component of uh, any leakage, and this cannot be ignored. इसको हम ignore नहीं कर सकते हैं. I hope this is clear. Okay. Having said that, next is oxide tunneling current. Now, normally what happens is in the present scenario, we have been reducing the thickness of the oxide layers considerably. हम काफी तेजी से oxide thickness को कम करते चले जाते हैं. And reducing the thickness obviously would result into what happens? Damage. Because we also know that uh, uh, the potentials which we are applying, that would result into a high electric field. So any high electric field with a reduced oxide thickness would result into tunneling. So reduction of gate oxide thickness will result in increased field across the oxide, resulting in tunneling of electrons from substrate to gate and vice versa. And this is something which is very important as regards with the reduction in the oxide thickness is concerned, because we cannot go ahead and reduce just the thickness for the sake of reducing it. No, you have to analyze it. You have to see whether reduction in the oxide thickness would result into further degradation of the performance, and if so, and this is true, and if it remains so, then obviously alternative mechanisms have to be thought of, and the alternative mechanisms here are using a hafnium oxide, or hafnium oxide, which further increases the or reduces the tunneling through the oxide layer. Gate current due to hot carrier injection. Now, let us understand this very uh, uh, important effect. These are all short channel effects. I think you all must be very much aware of, but these are all short channel effects, and we are discussing here in terms of the leakage currents. So gate carrier due to hot carrier injection. Now let us see what is this. what type of leakage this introduces. Now, let us imagine for a moment that in a MOSFET, when a high electric field is applied, obviously high electric field can be generated by application of potential to the drain. So when a high electric field is applied to the drain, what happens that uh, due to this high electric field, the electrons or the carriers scatter. When they are moving from source towards the drain, they scatter. And when they scatter, what happens? They move in a waveguide way, and some of these carriers or electrons moves towards the silicon dioxide silicon interface to the surface. Okay, silicon dioxide and silicon surface. Now, at this surface, please note, at this surface, some of the dangling bonds may be present. Now, these dangling bonds are formed when a silicon dioxide layer is composed with the silicon layer, combined with the silicon layer. So at the interface, a dangling bond layer would be formed. So when the scattered electrons or holes, they gain sufficient energy and they move towards the surface channel surface where scattering due to scattering, what happens? They some of them lose their energy into these dangling bonds, and they sometimes and afterwards they gain some energy. So this way they start moving across the surface. Some of these electrons or the holes gain sufficient energy and they break the barrier silicon dioxide silicon barrier or the surface layer. They break this interface barrier layer and enter the oxide layer, and when they enter into the oxide layer they get trapped there because they cannot move uh, from there. And if this so happens, and if there are more number of carriers which get trapped into the oxide layer, they may result into some hot carrier injection current. And this is what is known as hot carrier injection due to uh, the surface scattering sometimes due to the scattering of the electrons. They hardly move in the right direction. They move towards the interface, strike the interface, and they tunnel the interface, move to the other side, and get trapped into the oxide layer. And this trapping of the oxide layer is known as hot carrier injection. And these carriers may result into some gate current flowing through the oxide layer into the device, which is known as gate current due to hot carrier injection. This is what I was referring to when we discussed I3 and I4. Now I5, gate induced drain leakage. Again, this is also dependent on the high electric field which we apply. Okay, and as you can see here, it's already written down there that when a negative gate bias is applied, when a negative gate bias is large than the n plus drain region under the gate, can under the gate, this can be depleted, even inverted. This results in increase in high field effect, such as avalanche multiplication and band-to-band tunneling. The minority carriers are then emitted in the drain region underneath the gate. These are then swept away to the substrate, completing the path for GIDL. Gate-induced drain leakage. This I5 we are discussing. Gate-induced drain leakage. Okay, so due to the application of this negative bias, this effect occurs and this results in high electric field. Okay, due to which what happens? Avalanche multiplication and band-to-band tunneling may happen, and obviously the minority carriers gets emitted to the drain region, thus resulting into the GIDL effect, which is gate-induced drain. And similarly, I6, the channel punch-through current, when the combination of reduction of channel length and reverse bias lead to merging of depletion regions, punch-through occurs. This is very simple, and everybody knows what happens. We know that due to the shortening of the channel length, what has happened lately is that the transistor size has reduced considerably. Now, when the transistor sizes have reduced considerably, that have brought both the source as well as the drain closer to each other. Now, when the source and drain have been brought closer to each other, obviously, when the devices start to operate, the depletion regions would also be there. Now, due to the depletion regions, what it so happens that the depletion regions almost merges merged uh, uh, together. Under that circumstances, what will happen? Punch through will occur. And this punch through is also a type of leakage which is undesired, and this has to be avoided. And this results only when the two depletion regions merge in the channel region. So these are some of the disadvantages, though they are disadvantages, please note, though they are disadvantages, but still a lot of research is going on because we have seen the limitations. These are all limitations. And since they are all limitations, so these limitations have to be overcome. Now, limitations of size and dimension is something which is now getting more and more trickier because the channel, where would you further go and reduce the channel length? The channel length now has become almost comparable to the mean free path of the carrier which is being fed. So electrons, any electron which would actually travel a mean free path before getting recombined. So that much of length also you are not leaving on the table. So this would result into lot of complexities. That is why researchers, designers, and engineers are working hard to crack some other alternative mechanisms by which the technology advancement does not stop and it continues. So subthreshold current, obviously, we have already seen this, so no point in continuing with this. Subthreshold slope. The subthreshold slope is much sharper with the reduction in oxide thickness. The subthreshold slope is sharper with increase in VSB. The threshold voltage increases with increase in I off. Therefore, subthreshold swing also increases. Subthreshold swing also increases with the increased doping density and reduced gate strength. Okay, just a minute. I'll take a sip of water and then I'll continue. Just. Okay. So now returning back to our topic. We have seen that leakage reduction, actually the total leakage power consumption in any circuit broadly can be divided into two categories: static power consumption as well as dynamic power consumption. Now, important thing to note is that in the current day scenario, when the devices have become very small and these devices are operating at humongous frequencies, very high frequencies. The power consumption, the dynamic power consumption, as well as the static power consumption, total power consumption combined would be very high. So as you can see from the equation which has been given there, the dynamic leakage as well as the static leakage, if we just consider the dynamic leakage equation, we can make a statement that the dynamic leakage power actually is very much directly proportional to the operating frequency. So that simply means that the operating frequency is pretty high. Operating frequency is pretty high. Now, if the operating frequency is high, what will happen to the power dissipation? Power dissipation would also be high, would be substantial. It's a very important component. Just recall, when the devices were long channel, under that circumstances, the two components, the two leakage components were present at that time also. And we had stated that the static leakage current actually was more as compared to the dynamic leakage power. So the static leakage power consumption in the circuit was more, and the dynamic power consumption in the circuit was less in long channel devices. And on an average, it was found that almost most of the power consumption was due to static. Almost 85 to 90%, please note. Whereas dynamic leakage, dynamic power consumption was only 10 to 12%, not more than that. But the scenario has completely changed now. In the present day scenario, the dynamic power consumption has considerably increased. Static power consumption is also there. It's a very important component. Please note. Static power consumption is also a very important component. But dynamic power consumption in the circuit has increased considerably lately with short channel devices. And the most important attribute to this is the devices operating at pretty high frequencies. So when these devices are operating at such high frequencies, the dynamic power consumption increases at an alarming rate, at a very fast rate. So that has to be contained. And I hope everyone understands the difference between dynamic power consumption and static power consumption. Dynamic power consumption is that power consumption when the device is changing its state from either 0 to 1 or from 1 to 0. Under state of transition, the power being consumed under state of transition is your dynamic power consumption, whereas static power consumption is the power being consumed when the device remains in a stable state of operation, either at logic high level or at a logic low level. So this is the difference. So we know that static power consumption is a continuous form of power consumption which continuously happens in the circuit. That is why it is said that static power consumption component wise is larger as compared to dynamic power consumption for long channel devices. But now with short channel devices, that has become comparable now. So you can very well see that how the dynamic power consumption in the circuits have considerably increased. Okay. Static power consumption, अभी जो हम लोगों ने पढ़ा है leakage currents, all these leakage currents would constitute static power consumption. Please note, all the currents, the leakage currents which we have studied just before this slide, they all constitute the static power consumption. Okay. Now, how these leakage can be reduced? So reduction techniques have been shown here. They can be achieved through process level technique or circuit level technique. So process level technique, obviously different by using different processes. Leakage can be reduced. Leakage reduction can be achieved by controlling the dimensions and doping profile in transistors. Some of these techniques are briefed below. Retrograde doping. Now, this retrograde doping is a vertically non-uniform, low, high channel doping. It improves short channel effects and increases surface mobility by creating low surface channel concentration followed by highly doped subsurface region. Okay, so this retrograde doping is a vertically non-uniform low high channel doping. Okay, I hope you understand. Vertically non-uniform, it means the doping is non-uniform vertically. Okay, so this is known as retrograde doping. Then we have halo doping, or non-uniform channel profile in a lateral direction. So in a lateral direction from source towards the drain, a non-uniform channel profile is made, and this is known as halo doping. This had become some famous for some certain applications, but normally, yes, researchers are using this for certain applications. So it is in continued use today. So this halo doping or non-uniform channel profile is a lateral direction doping, and this was introduced to provide another way to control the dependence of threshold voltage on channel length. Okay, so this is another type of process level technique. Now we come to the circuit level technique, and these are more important because the process level techniques, once the process level techniques, they can only be considered when the device is in manufacturing state or when the device is being manufactured. So the device is already manufactured now. Now, once the device has already been manufactured, now, in that context, circuit level techniques becomes more important because it's by somehow or by some means, if you can reduce the power consumption in the circuits by circuit driven techniques, then those would be of more use. So some of the circuit driven techniques by which the these power consumption can be reduced or the substantial leakage currents can be reduced have been mentioned here. So let us say first the transistor stacking. Now, subthreshold leakage current flowing through a stack of series connected transistors reduces when more than one transistor is turned off. This effect is known as stacking. Stacking is a very well-known fact, and this is a process in which the transistors are stacked or they are connected in series. When they are connected in series, what happens? Obviously, this stacking effect reduces the threshold voltage because any one of the series connected transistor, when they turn off, the obviously the leakage can be cut off. So any this subthreshold current which is flowing can be cut off, and this effect can very simply be understood as stacking effect. Multiple VTH design techniques. Yes, this is another which has already gained a lot of momentum, and lot of engineers are using this multiple threshold voltage techniques. It means you have a single transistor and you are making your device operate at multiple threshold voltages. How can we achieve multiple threshold voltages? This is a question which may come to your mind instantly, isn't it? So all of us know that the MOSFETs use a fourth terminal which is called a bulk terminal. When the MOSFETs use the fourth terminal, the bulk can control the threshold voltage of the device. Please note, the bulk can control. So that is why bulk terminal is also known as the second gate terminal, because it is the gate terminal which has got all the controlling capacity of the MOSFET, or it is also known as the controlling terminal. If you remember correctly, MOSFETs, the gate terminal is known as the controlling terminal. But here, when we are using the bulk terminal or the fourth terminal, this fourth terminal actually uh, uh, reduces the controlling effect of gain. And in fact, this acts as a second gate terminal by which the threshold voltage can be modified, can be moderated, can be increased. So this, by using this bulk terminal, the threshold voltages can be altered. Okay, I hope this you can understand. So multiple VTH techniques can be obtained by some yes process techniques also, like multiple channel doping, multiple gate oxide thickness, multiple channel length, multiple body bias. In those, MT CMOS, multi threshold CMOS, DT CMOS, dual threshold CMOS, DT MOS, dynamic threshold MOS, VT MOS, variable threshold MOS, DT MOS, double gate dynamic threshold MOS. So these consider all. Some of them are process driven, and some of them are obviously different types. Multi CMOS, multi threshold CMOS, dual threshold, dynamic threshold, variable threshold, and double gate dynamic threshold. So these are all circuit-based techniques by which multiple threshold voltages can be obtained. So these are some of the dynamic threshold voltage designs: VTH hopping scheme, dynamic VTH scaling scheme, and supply voltage scaling. Scaling we have already seen, so I don't think, yes, we have seen this. Now, high K dielectric. Now, as I've been mentioning here, that normally what happens is the oxide thickness, the oxide are getting scaled. Now, when the oxides are getting scaled, what is happening is that the tunneling effect creeps in. Okay? And due to which what happens, the leakage currents also increase. Tunneling की वजह से obviously क्या होगा? Leakage current तो increase होगा ही. So the alternate to this is replacing a high K dielectric in place of silicon dioxide. And if this high K dielectric is used, this allows the increased gate capacitance without leakage effect. It means if we are using this high K dielectric, obviously this would result into increased gate capacitance. And if this gate capacitance increases, what happens? The leakage due to due to tunneling can be prevented. So high K stands for high dielectric constant, which is a measure of how much charge a material can hold. Okay, I hope this is again clear. Now, fringing capacitances, obviously, this is, as the name itself, you can very well understand, this is a byproduct of this technology, and obviously the scaling. And normally this occurs when the W to width to thickness reduces to almost unity. Width to thickness, plate width to thickness, please note. When this reduces to almost unity, under that circumstances, fringing capacitances occur. Okay, and what does this mean? This means that the width of the material is comparable to that of the height. Width is comparable to height. When this happens, we need to consider capacitive effects due to sides also. Hence, fringing capacitance is usually taken as twice of the capacitance value of the device. And normally this fringing capacitances occur at very high frequencies. ये काफी high frequencies पे you can find them. This is the basic MOS structure. This is the basic MOS structure. I think all of you are very much aware of it. And these are the various capacitances which are associated with MOSFETs, as you can see here. All these capacitances have to be modeled. These capacitances are important and they need to be modeled. Modeling these capacitances is important for analog devices, not for digital devices or for digital operations or digital circuits. So for digital circuits, only the gate capacitance is important, and other capacitances very safely can be ignored. But if we are considering analog analysis or analog design, Under that circumstances, all these capacitances have to be taken into consideration and they have to be properly modeled. So, and this is what this is the description of the various capacitances which are shown here. C1 is the outward fringing field capacitance between the gate and the source. C2 is the direct overlap capacitance between the gate and the source. C3 is the inner fringing field capacitance between the gate and the sidewalls. C1, C1, C2, C2, C1, and C3, this one. Okay, I hope now you understand. C3 is the inner fringing field capacitance between the gate and the sidewall of the source and drain regions. The capacitances have been shown here, so I won't go into greater detail. And yes, now I come to a very interesting fact here. Until now, we have been looking at the conventional device or conventional device structure. So, yes. So, what we understand here is that the conventional device, conventional MOS device, obviously is well known to all of us. But now, unconventional device structures are also gaining a lot of momentum. And when the short channel devices have created, under that circumstances, unconventional device structures have gained a lot of prominence, and they have also got a lot of attention. So let us see how these, what are these unconventional structures? They can be broadly divided into SOI, silicon on oxide insulator, SOI, partially, SOI can be further broadly divided into partially depleted SOI, fully depleted SOI. Then multiple gate transistors, obviously double gate transistors, there may be others also, and FinFETs. FinFETs again is a very promising device, which is lot of which has gone through uh, turns, and now it's getting stabilized, and now researchers have found good results, good structures to work on. So FinFETs, double gate FinFET, triple gate FinFET, gate all around, etc. So these are some of the unconventional structures which have gained a lot of momentum, and a lot of researchers are working on them. So this technology roadmap, obviously this is a very old one, but this has almost remained same, but expanded to a very short channel device. Devices have more or less remained the same. The only difference here is that the year here it's showing only up to 2012, but even if you extend this to 2020 or 22, you will find that more or less the devices remain the same. The only difference being that the size have considerably reduced. Size of the device have considerably reduced. So scaling, we have already discussed. So I won't be going into, yes, some of the figure of merits of scaling: minimum feature size, number of gates on one chip, power dissipation, maximum operating frequency, die size, production cost. These are, this is the impact of scaling on the various indicators. And this is how scaling, yes, full scaling, fixed voltage scaling, general scaling. I've already described some of these, the scaling factors. Normally we use two scaling factors, alpha and beta, okay, for in order to scale all other dimensions, alpha and beta are used both, whereas in order to scale power supply and oxide thickness, only beta is used. This is what has been shown here. And these are some of the parameters and their effect on the constant field scaling and constant voltage scaling. And this is how this has been represented for various parameters, how these various parameters are affected. Actual effect of scaling, again, we have already discussed this. FinFETs, yes, we have seen that in short channel devices, the gating is losing some of its control, so that control has to be regained. So FinFETs is an answer to that. gate FinFET. These are some of the advantages of FinFET's robustness, high current drivability, good threshold swing. These are some of the structures, cylindrical and partially cylindrical. These are some of the non-classical CMOS structures which have been shown here. Ultra-thin body, band engineered transistor, vertical transistor, FinFETs, double gate transistors. And these are some of the problems associated with these devices and how they can be taken care of. So some of the solutions also have been shown here. Yes. So thank you, everybody. This is it from my side. If you have any questions, please go ahead. I'm there to
Hello.
Yes.
Good afternoon, sir.
Yes, good afternoon.
Thank you for a nice presentation. That chart of scaling was very nice, sir. Thank you for that chart.
Okay, thank you.
Sir, I have one doubt. Sir, you told about that dielectric with high K. But in that case, what I feel is the gate capacitance, if it is increasing, then turn on time will also change. And that may lead to the dynamic
Shishma,
losses.
can you be a little bit louder because I have a hearing.
Yeah.
I
Am
cannot
I
hear
audible,
you.
sir?
Yes, yes. Go ahead now.
Sir, when we are using a dielectric with high K, that will obviously increase the gate capacitance. And if the gate capacitance is increasing, then the turn-on time will increase, and that may lead to the dynamic losses. So, if we are trying to reduce the leakage current, then these dynamic losses, if they are increasing, then how can we again optimize the losses?
No, no. You are talking in the context of reducing the oxide thickness, isn't it?
No, I'm talking about increasing the dielectric strength. You told about using
Yes,
use of
dielectric strength. Yes.
yes. If we are using a dielectric material with high K, you just now told.
Right, right, Shushma. Understood, understood.
Yeah, then the gate
So,
capacitance is increasing, sir.
yeah. What
Obviously,
you're
it will
saying is
increase.
that under that circumstances, leakages would increase, isn't it?
Yes, so dynamic losses they are going to
Right,
increase
right.
because turn
Understood.
on time will increase and
But here we need to understand that if we are not using a higher dielectric constant under that circumstances, the thickness have been forced to reduce. Under that circumstances, what will happen? Tunneling will take place now.
yeah,
And if tunneling takes place, a larger leakage current would flow. So in comparison to that, even if you are using a high K dielectric, and even if you have a little bit increase in
dynamic
the
losses
dynamic losses, that obviously
can be bearable. Okay.
optimized result can be obtained.
And you told me, sir, that in some cases for the analog design, we may ignore the modeling of few capacitors.
Yes, yes.
So,
Not analog, Shushma. I
sir, for
said
digital, hello,
yes, Shushma. Yes, go ahead.
sir, you told that for analog designs, we can ignore the modeling of few capacitors.
No. If I said that, that was not correct.
Uh,
Actually, I was saying that for digital circuits, most of the capacitances have to be ignored except the gate capacitance.
Exactly, sir. Because for digital means if the frequency of operation is very high, then
Yes,
modeling of your capacitance can be ignored.
yes.
So,
So if I said analog at that instant, that was not correct.
yes, thank you.
Okay. But in analog, you have to consider all the capacitances, and
Yes,
all capacitances have to be properly modeled, and analog analysis have to be done. So
okay,
we cannot ignore the capacitances in analog devices. Please
okay.
take.
Thank you, sir.
Thank you.
Thank you so much.
Thanks a lot.
Excuse me, sir.
Yes.
Sir, I have one doubt, sir.
Yes.
Sir, you had told high performance VLSI circuits. What are the parameters to be considered for a VLSI circuit to be high performance, sir?
Ramani, I cannot hear you properly. Your
Sir,
voice is not clear.
when a VLSI circuit is said to be high performance circuit, sir,
Yes.
Under what condition we can say and VLSI circuit to be a high performance circuit?
Under what circumstances we can say that the device's circuit is high performance? This is what you're asking?
Yes. Yes, sir.
Okay, you see, when we are discussing about the high performance of the circuit, the important becomes that the device should operate at high drain currents. So whenever we are discussing with high performance, and under that circumstances, the power consumption of the circuit would be high, because if we require high performance, our the gain of the circuit would be large, should be high. All the performance parameters should operate at inversion regions, at strong inversion regions. So when the device is operating at strong inversion regions, only then you will get a high performance circuit. So under that circumstances, the power consumption of the circuit would be a little bit higher, on the higher side. So always remember that high performance circuits always result into higher power consumptions.
Okay, sir. Okay, sir. Thank you, sir.
Thank you.
Sir, can I ask one more small doubt I have?
Yes, Sushma.
Sir, we are throughout the session we were talking about the short channel devices.
Yes.
But if we are talking about width and length parameters of the channel, then that means that is going to have the body effects also. So how can we avoid this body effect in these short channel devices, sir?
How can we
Avoid? What are the different techniques we can use?
Okay, Sushma, understood. If I have understood correctly, then what you're asking is how can the body effects can be avoided?
Yes, sir. Yes.
Sushma, frankly to say, it's very difficult in present day scenario to avoid the body effect in short channel devices. They have become almost integral part of the circuits.
Exactly,
So,
because this is the major constraints every designer
yes,
is facing.
yes. You have, Sushma, you have to use the fourth terminal, isn't it?
Yes.
Without using the bulk terminal, you cannot control. Actually, the bulk terminal has become the second controlling terminal apart from the gate terminal.
Yes.
So if you have to alter any threshold voltage of the device, because threshold voltage is the most important parameter of any circuit analysis or circuit design. So if you have to consider varying the threshold voltage, obviously the bulk terminal is required and the body effect creeps in.
Yes. Thank you. Thank you.
Thank you.
Any other question from the participant side? Okay. Good evening to our learned speaker, guest, Dr. Sanjeev Rai, Associate Professor, MNNIT Prayagraj, and the participants. I, Pushpen Kumar Gupta, on behalf of the Institute I.E.R.T. Prayagraj and the entire team of this Atal Fdp, and on my own behalf, extend a very hearty vote of thanks to Dr. Sanjeev Rai for this extremely informative session. This extremely fruitful and informative session cover many fundamental and advanced things related to VLSI design with leakage control and low power design issue. The words are not sufficient to express our gratefulness to Dr. Sanjeev Rai sir for sharing his knowledge and research findings with us. I hope this session must be helpful not only from research point of view, but also from academic point of view to all the participants. We offer sincere thanks to all the participants also for making this session successful. Thank you once again, sir, for your such a nice talk.
Yes, thank you, Dr.
sir.
Gupta.
Thank you, sir.